everyone. It's great to be here connecting with everyone in Europe and the entire robotics community. I'm Carolina, and I lead robotics at Google DeepMind. I'm going to be talking today a bit about how Gemini can power the next generation of helpful robots. I think we all agree in this room that robots today are doing incredibly useful things. They're helping in manufacturing lines, they're in logistics, in automotive, they're navigating our moon, and they're even doing really cool acrobatics. However, these robots have been programmed to do these particular task sequences. They make a lot of assumptions about everything in their environment, every object that they touch, or they might be remotely operated by humans. This makes robots today incredibly bespoke still, and difficult to deploy, often taking many months in order to deploy a new application or a new task, only to have to do it all over again when something changes about the task. At Google DeepMind, we've always believed that AI will transform robotics. So we've been at the forefront of building foundation models in order to build and enable truly intelligent general-purpose robots. What we mean by this is robots that can go on any environment, that can operate across many different verticals, do a broad range of tasks, and handle objects they have never seen before. We also mean robots that are intuitive, so anyone in their environment should be able to task the robot, adapt the robot, improve the robot. This also means robots that are safer, because they understand what they're trying to do, they understand the context in which they're operating. If anything changes, they can adapt because they understand what has changed. And these are robots that are drop-in, that they come with a broad range of skills that can adapt to objects and environments. And more importantly, they don't need to know everything from the start, because they can learn and improve over time. This is what will transform robotics from one application at a time to the ultimate tool for humans in the physical world. And this is what we care about at Google DeepMind. Our mission at DeepMind is to build AI responsibly to benefit humanity. And in the robotics team, our goal is to bring this mission from the digital screen into the physical world in a way that is helpful, that is safe, and that is empowering. In fact, our goal at Google DeepMind is to nothing less but to solve AGI in the physical world. What does that mean anyway, to solve AGI in the physical world? Well, it means that we want to build an AI that can infuse a robot with human-level intelligence and physical abilities, so that robots can understand the world and reason about it the same way you and I can. Not only that, but also take action to the precision of a human expert. It also means building an AI that can go into any embodiment. We believe in a world where there will be many different robot types, each one of them evolving over time and becoming a different robot. And you want this AI to basically adapt and maximize the potential through intelligent control. And lastly, you want an AI that can be deployed in the real world. So it needs to handle all the diversity and the noise and the unstructuredness and the ever-changing environments that live in the real world in order to bring real, tangible impact. This is, of course, a very ambitious goal, but one that we've been after since the inception of the team. And over the last few years, we've introduced significant advancements that have become table stakes in the field of general-purpose robotics. For example, in 2022, we introduced LLMs and VLMs into robots. This was the first time that robots were able to really understand semantically their environment, understand objects, and plan using multimodal input. We've also introduced transformers into robotics. This ushers a new area of data-driven robotics. We've also introduced, in this set of work, the concept of a VLA, or a Vision Language Action Model. That enables robots to understand natural language, understand their environment, and do more general actions. And we've also shown what's possible when it comes to actually, let me go to the next one. We've also shown what's possible when it comes to learning highly dexterous behaviors, like in the tying shoelaces example, something we didn't think we would see in our careers, as well as introducing reinforcement learning and simulation for whole body control. And we've shown this on quadrupeds and little humanoids playing soccer and on ping pong robots. And this is now the default for whole body control in the entire industry. Last year, Building on this, we introduced Gemini Robotics. This is our most advanced visual language action model to power the next generation of helpful robots. Gemini Robotics, as you can tell, it draws from Gemini's multimodal world understanding and brings it to the physical world by adding actions as a new modality in Gemini. So the same way that Gemini can produce text and code and images, it can now produce robot action sequences, which are essentially trajectories that move the robot in a way that is general, that is interactive, and that is dexterous. The reason robots are not all around us here today is because they cannot handle generalization yet. If you change the robot complete environment, you change the task that it's trying to accomplish, you change the objects that it's interacting with, typically it falls apart. With Gemini Robotics, the idea is that they can use Gemini's world knowledge in order to tackle a completely unseen situation. A good example that I like to showcase this is this example coming up right now on the right, the basketball hoop. So this is a toy that our video team brought that day. So the robot had never seen this toy. It's never seen anything related to basketball. And our team asked it to slam dunk the basketball. Even though it's never seen that object, it's never seen that kind of task, it took a quarter of a second to decide that meant put that small ball into that basket. That is the kind of generalization that we care about. We also introduced, with Gemini Robotics 1.5, agents into robotics. The reality is most tasks in the real world are complex, and they take multiple steps to complete. In order to do this, we need to move beyond single instruction following, which we can now do in a very general way, into agentic systems. This means that it needs to be able to understand what the human is trying to do and then translate it into a sequence of steps using whatever tools are available to it, including VLAs. Let me just show you a quick example of what this looks like I'm not sure it's going to be audible, but we'll see.
Hi, Aloha. Can you use my location and sort the objects into the correct compost, recycling, and trash bins?
To perform the sorting task based on San Francisco waste guidelines, I will use the green bin for compost, the blue bin for recycling, and the black bin for trash.
Here we have on our agentic layers, both control the robot and have access to the internet. To sort the trash, they had to look up the rules and look at the objects on the table, think about where each object should go, matching the rules that they had looked up.
Can you guys hear me now? OK, cool. So what you're seeing there is essentially an agentic system that is powered by two key AI models. A high-level reasoning layer called Gemini Robotics ER. That's our agent that understands the environment, understands the natural language, and it can speak back to the human and reason about the sequence of steps to take along with the VLA. It can also use tools. As you saw earlier, it was pulling up from search what are the rules to do that task on trash sorting. Let's talk a bit about this model more. So this is a physical agent with memory. On the left, you're seeing someone asking the robot to reset the scene after making a bunch of changes in that scene. So it has to remember what the scene looked like. It has to understand what it means to reset the scene, and then carry out the sequence of steps in order to achieve it. Many people also use this model simply as a perception layer or a reasoning layer. So you can use it for 2D bounding box detection, 3D bounding box pointing. You can ask to match all the socks on that image on the right. We've also, last month, introduced Gemini Robotics ER 1.6. This is our safest and most advanced model for robotics to date. In this model, we're advancing 3 core capabilities: pointing, enhanced success detection, as well as a new capability called instrument reading. Pointing is a pretty basic capability for spatial understanding. You can use it for identify all the objects in the scene, count the hammers in the scene. But you can do more complex queries, like find me all the objects that fit in a backpack. What you can see here is the evolution of the model only in the last 9 months or so. And you can see that the model is now a lot more confident about what's in the image versus what's not. It's also more confident exactly how many objects are in that image. This is extremely useful for cluttered environments in examples like logistics, where your task is to pick up just the top thing that is on that pile, or the top 3 things. Another capability I'm incredibly excited about is instrument reading. This is a capability we discovered with our partners at Boston Dynamics, the SPOT team, who does inspection in all of the industrial facilities, and they want to read all the instruments. This model has advanced instrument reading thanks to something called agentic vision. What that means is that the model can decide if it wants to read this gauge, it can take intermediate steps. It can decide to zoom into the image to get a better reading of that gauge. It could then decide to use pointing and maybe code execution in order to do some math and figure out the exact value of each interval in that gauge. And then once it has a very accurate reading, it can use its world knowledge or call another tool to decide whether that gauge is within normal reading. This is what we call agentic vision. And in the last, again, 3 to 6 months, it's dramatically improved. We're now about 93% performance on this test set, and these are real images. You can see they're very diverse, they're noisy, they're small. This is from real-world examples. And then in combination with Boston Dynamics, we deploy this on their robots, so now all of their customers are able to use this. So we're basically integrating our Gemini Robotics ER reasoning layer with Boston Dynamics autonomy system in order to enable it to do understand the environment, understand every object, read every instrument, and then interact with the environment as they normally would. And now Spot can also use Gemini capabilities. It understands natural language. It can read that board. It can do the full sequence of tasks and orchestrate them. And I guess apparently it can take Coda for a walk as well. Our goal is beyond the quadruped robots to also integrate with Boston Dynamics. Yeah, I'm not sure who's walking home there. Our goal is to also integrate with Boston Dynamics humanoid robot Atlas in order to bring Atlas reasoning and action capabilities and really fulfill that promise of true general-purpose humanoids. Let's talk a little bit about the VLA. This is our action model. As I mentioned earlier, it takes visual input, typically all the cameras available to the robot. It takes natural language input as a prompt. It could also alternatively use proprioception or previous actions. And the output is directly the robot control targets. This can be specified different for different robots. Sometimes they're the end effector positions. Sometimes they're the full joints of the robot. And then that typically goes to the motor controllers who translate that into motion. With that model, we can control all of these different robots. So this is the Franca Bayam robot, the Aloha robot. We also can control the Aptronic humanoid robot. And in all these cases, it's doing a broad range of tasks. It's responding to natural language requests. So it's interactive and it's dexterous. In the case of a humanoid, since I mentioned the Apollo robot, it looks a little bit more like this, the picture. So if you go and ask a robot, hey, could you please put my groceries away? What it will do is it will first send that to the ER model, which is the agent. It understands the environment, it understands the input, and then translate that into the first step to take. Then say that it says, OK, the first thing is to take the baguette out of the bag. It will then go and send the text string, take the baguette out of the bag, proprioception and perception to the model, and the model will output the trajectories to do this, right, and take it out. And then underneath, there's a whole body controller. It's an RL policy that is, of course, tracking that VLA and ensuring that the robot stays stable. The other thing is that these models also have thinking. What that means is that the model is generating text and action tokens together. And that enables it to reason about what it's doing. So in this video, I have no agent. It's just the VLA. Let's see what it plays.
Previous Gemini Robotics version has been tested over and over and over again to put this banana into the bowl. This is a very simple task. I'm going to switch the model here and make the task slightly more challenging. So this is Gemini Robotics 1.5. Aloha, could you sort these fruits into color matching plates?
Sure, I can certainly help you do that. Put the green fruit into the green plate.
We enable it to think. It can perceive the environment, different colors of the object, different colors of the plate. It would think step by step and then finish this multi-step task.
Put the banana into the yellow plate.
at that. We have a lot more examples of that if you go into our website. The last piece is that these models can work across embodiments, as I mentioned. And not only that, they can learn across embodiments. So what I have here is the same set of weights working on these 3 different robots. And on the top, you can see how the robots get better. This is the Apollo robot in blue after learning from Aloha. And this was because we had very little data at the time on the Apollo robot. And you could just learn from the stuff that Aloha had already learned. All right, I'm going to go very quickly since I have a few minutes left. What is at the frontier? Certainly, one of the things we're working on is how to scale learning. Everything that you've seen today is essentially learned through robotics teleoperation. That means a human had to put on goggles and gloves and was able to move the robot to teach it how to do a task. That, of course, only scales with the number of robots and the number of hours that you have in the day. We've also would like to learn, of course, from videos, the same way humans do. We learned a lot from watching others, and then we practice a little bit. That's the ultimate goal. We are always working on that. And then we also have areas in the middle. Like you can learn from simulation better. You could dramatically increase the number of environments that you have. You can learn from world models. I'll just mention just a couple of these examples. So today, we have a long history working in simulation with Mujoko, but today we can now enable completely new task families and actually onboard completely new robots in simulation first for manipulation, which was not the case before. And this helps us accelerate generalization. We've also have world models now. What I have here is an image from Aloha on the left and another from Aloha on the right. One of them is real, one of them is generated. Anybody cares to guess which one is generated? The left one. Anybody? Nobody. Right. One person. All right. So they were right. The right one is generated. And more importantly, it's just getting extremely hard to tell which one it is. So in fact, in our team, we always put a border around videos that are generated, because it's now hard to tell. So we can use this, of course, for data generation, for all kinds of different research threads around world models. And we also use it very much on evaluation for safety policies. So as you can imagine, we take world models, make them look like the input is coming from a real robot, then condition it on actions, and actually roll out policies in that environment. And then you can use it to do all kinds of different scene evaluations. You can use it to put hard situations that you don't want to do in real, like put your hand in there and see what happens, put a baby in there and see what happens, and it's all good. This is excellent for safety evaluation. The last piece is that obviously models alone are not going to change the world. You need to combine them with real robots. So we're extremely grateful for our partnerships with Boston Dynamics, Agile Robot, and Aptronic. And we're working together to advance the state of the art on general purpose robots for humanoids in particular, but also other robots. And then we also have a trusted tester program. Many companies here in the EU are in it. There's actually a lot more than what shows here. We've been working with Enchanted Tools for a while. Generative Bionics is also there. Bubble Robotics is also there. There's quite a few. PAL Robotics is also there. And then we now started the EU Accelerator to help bring many different startups in the EU into robotics and get them closer to understanding how AI works and accelerating AI in their companies. Now, many people ask me what the futures of robotics looks like. I'm sure we all here are dreamers. I'm extremely bullish when it comes to it. It really depends how much effort we're putting into really making this valuable for humanity. Because that's what matters at the end of the day. And AI is going to accelerate this. It's going to make robots more intuitive, more general, more multi-purpose, safer. Of course, I also believe the best way to predict the future is to invent it. So I'm incredibly excited to be working in robotics today. This is the best time to be working in robotics, and very excited to be collaborating with all of you to make this future possible. Thank you very much.